Assalamu alaikum wa rahmatullahi wa barakatuh. So, resume with the topic of nonlinear pharmacokinetics. Uh, just a quick review. Up till the previous part that we discussed a few minutes ago, we always put the assumption that the drug is following linear pharmacokinetics. And we said that linear pharmacokinetics means that if we plot the dose given against the resulting concentration, we will find a linear relationship. Means you double the dose, you get double CP. You triple the dose, you give triple CP. And if you remember, we mentioned that all the time in linear pharmacokinetic model, elimination was first order elimination, right? So you remember these two things. When it comes to linear pharmacokinetics, elimination is first order. There is linear relationship between dose and concentration, resulting concentration from the dose. What concentration you fix? You give different doses and then you measure the concentration at the same time, either at time 0, 2 hours after the dose, 4 hours after the dose, whatever. Just you measure the concentration at fixed time. And then you plot against the dose, you should get a linear relationship. Okay? However, in nonlinear pharmacokinetics, situation is different. Okay? What are the characteristics of nonlinear pharmacokinetics? Number one is dose-dependent pharmacokinetics. Elimination kinetics are non-linear. Okay? How? Increased doses or chronic medication can cause deviation from linear pharmacokinetic profile observed with single low doses of a same drug. How also pharmacokinetic parameters for a drug will change when different doses or multiple doses of that drug are given. So, for example, in linear pharmacokinetics, elimination rate constant all the time was constant. You increase the dose, you decrease the dose, still the elimination rate constant is the same. However, here you will have different values for pharmacokinetic parameters if you change the dose. The area under the curve also will not be proportional to the amount of drug that is given. Means if you multiply the dose by F and then you plot dose versus AUC, dose times F versus AUC, or versus CP even, will not give a linear relationship. The relationship may be nonlinear, up or down. Okay? The composition and or ratio of metabolites of a drug may be affected by the change in the dose also. For example, you have metabolite 1 and metabolite 2. At certain dose, the ratio between them is 2 to 1. You increase the dose, probably you may get a ratio of 1 to 1, whatever. You'll have a different ratio. Okay? These are the characteristics of nonlinear pharmacokinetics. So as I mentioned, if you plot the dose against the resulting concentration at fixed time, say steady state concentration, Cmax, Cmin, or C random at fixed time, against the dose, if there is linear pharmacokinetics, then you will get this line, linear relationship. So this one is linear, represent the linear relationship. However, nonlinear will be a deviation. At the beginning, the attitude will be same like linear pharmacokinetics, and then there will be deviation up or deviation down. What does it mean to deviate in this direction upwards? Means that when you increase the doses, you will get a higher than expected concentration. Higher than expected concentration. So here, for example, the dose is 200. Say the concentration is about 20. You double the dose, 400, you get about 40. You get double concentration. But here, 600 will not give you 60. 600 will give you probably 70. And then 800 will not give you 80. 600 here give how much? Give about maybe 80 or 90. 800 give you 200 plus, not 80. Okay? So means you get higher than expected concentrations. This kind of kinetics, we call it Michaelis-Menten kinetics. And the reason is saturable metabolism. So saturable metabolism, in case of some drugs like in phenytoin, theophylline, very important this one. Once you study phenytoin in clinical pharmacokinetics, then you have to use Michaelis-Menten equation for calculation. There is saturable metabolic pathway. So if enzymes are not saturated, you increase the dose in this range that before saturation, there will be a proportional increase in the rate of elimination, so concentrations also will increase proportionally. But after saturation point, the rate of elimination will be stable, zero order. So you increase the dose, rate of elimination will not increase, so you get higher than expected concentrations. Okay? Then there is saturable protein binding or autoinduction that may result in trend that will be downward, the movement of the slope will decrease, means that you get less than expected levels with the increase in the dose, means that you double the dose, you may get only 1.5 times the concentration. You triple the dose, maybe you get only double the concentration. So saturable plasma protein binding, this one in case of valproic acid, for example. Valproic acid is highly protein bound. So before the proteins of plasma are saturated, the percentage bound is same and the pharmacokinetics are linear. But then after saturation, what happens? Any additional dose will go to the free fraction. So free drug in plasma means available for metabolism, means elimination or metabolism or excretion, available for elimination. So elimination rate will be increasing more and more and more, not proportionally, but more than proportional, higher than proportional. So the levels will not increase in the same proportion. Same thing for autoinduction like carbamazepine. Carbamazepine is enzyme inducer. When we say autoinduction, means it induces its own metabolism. Induce its own metabolism. So you give higher dose, it will increase more the elimination, more than proportional. Okay? So then there will be a slight decrease in concentration with increasing the dose. So for our drug, how to know if the drug is following linear or nonlinear pharmacokinetics? To know this, we have to give different doses, and then we monitor the decrease in, either we make plot, dose versus concentration, or we monitor the decrease, the decreased trend for plasma concentration. So for example, like in this shape, so determined by administration of different doses of the drug and plasma level, time curve is obtained for each dose. Drugs that follow linear pharmacokinetics, there will be if you notice here, the scale is 1, the distance from 1 to 10 is the distance from 10 to 12 to 100. This is semi-log. So you give IV bolus dose, supposed to give a straight line in both doses if the drug following linear pharmacokinetics. So if the two doses give B and C, then this is linear. Right? But if what you get is that there will be a linear decrease in concentration for low dose and a nonlinear decrease in concentration in the higher dose, then this indicates nonlinear pharmacokinetics. Okay? So drugs following nonlinear pharmacokinetics shows the following. The slope of the plasma concentration time curve varies with the dose. And AUC versus dose plot also is not linear. If you plot AUC versus dose, in linear pharmacokinetics you get a linear plot, as you can see, but in nonlinear pharmacokinetics you get nonlinear plot. Okay? And same if you plot dose versus concentration at fixed time. It will give you also nonlinear plot, same as the previous slide. So in this lecture, we just focus on calculations related to Michaelis-Menten kinetics, and we explain it. So here in Michaelis-Menten kinetics, drugs with saturable enzymatic elimination process, as we say, these are the drugs that follows Michaelis-Menten kinetics. Elimination rate constant is not stable, not constant here. It changes with changing the dose. So we cannot use it anymore in the calculations because it doesn't have a fixed value. So we replace the elimination rate constant by another variable. Okay? So here the elimination proceeds as a first order process before the saturation point. Once reach the saturation point for the enzyme system, then the elimination all on the enzyme become all the binding sites occupied. So you increase the dose, you increase the concentration of the drug around. You cannot increase the number of molecules that will be metabolized at one moment of time anymore. So it will become stable, fixed. Fixed means zero order. So after saturation point of the enzyme, the elimination rate becomes zero order. So here the equation became somehow more complicated. It doesn't. In linear pharmacokinetics, we said elimination rate constant, elimination rate equal to K times D, or times V D times Cp, right? But here we have two terms, Vmax and Km. Vmax is the maximum velocity or maximum elimination rate the enzyme can give. Km is the drug concentration in the body at half Vmax. So experimentally how Vmax is determined, simply in the lab, you can have a set of test tubes, test tube 1, test tube 2, 3, 4, 5, 6, whatever. So you increase the concentration of the drug in the test tubes. Okay? But all of them, they have the same amount of enzyme. So you add the drug and then for a fixed time, you fix the time and then you stop once you add the drug, then the enzyme is going to degrade the drug, right? It will metabolize the drug. After a fixed time, you stop the reaction. You deactivate the enzyme. Maybe you can put something organic, like, for example, methanol or acetonitrile. It will denature the enzyme and deactivate it. And then you analyze each tube. You measure the difference between the amount of drug before and after. So you calculate drug eliminated equal to amount of drug before the addition to the amount you add, the amount added, okay, minus the amount remained after the metabolism. When you divide this one by the time, then you get the elimination rate of elimination rate. Okay, so we have different elimination rates. You have elimination rate in tube 1, elimination rate in tube 2, and so on. Then we plot, and we have different concentrations increasing from tube 1 to tube 6. So we plot concentration versus elimination rate. So we go to one point, another point, and then connect. What happens usually? The rate of elimination will be linear, will have linear increase at the beginning. You increase the concentration, there will be linear increase in the rate of elimination, but at some point then it will not move anymore. It will be stable. Okay? For example, starting from this concentration, the rate of elimination is equal. Became same, fixed. Then here is the maximum, this highest amount is the maximum rate of elimination. This is what we call it Vmax or Vm. You can write it Vmax or you can write it Vm. Some references are using Vm, some references are using Vmax. They are same. So the highest value for the rate of elimination is Vmax. How much is half? We said Km is the concentration where rate of elimination is half maximum velocity. So 20 divided by 2 is 10. So from 10 you just determine how much is the concentration. This is Km. Km is the concentration at half Vmax. So this is experimentally how they determine for certain drug what is Vmax and what is Km. Or you give different doses to an individual and then you calculate Vmax and then you calculate the rate of elimination and how much the concentration of drug with each rate of elimination, and then you plot and then you do the same procedure. Okay, so let's see here an example of Michaelis-Menten kinetics. Hypothetical drug have a value of Km 0.1 milligram per ml. This is the concentration units, and Vmax rate of elimination means amount divided by time, so milligram per and Vmax should be milligram per minute. Okay, should be milligram per minute, amount per time. The rate of elimination, or say milligram per hour. Okay, then we use the same equation that we previously mentioned, this one. We calculate the rate of elimination. We substitute with the value of Km, Vmax and Km with different drug concentrations. So we vary the drug concentration from 0.4 up till 11.6. Let's calculate elimination rate. And we divide the ratio between, we divide elimination rate by concentration. We calculate the ratio. So if you see elimination rate is increasing, and then at some time, at certain concentration, the elimination rate will not increase anymore. Okay, it's almost stable at 495, 496. So this is the Vmax. This is the Vmax, almost 0.5, right? Almost 0.5. But if you calculate the ratio, then they find that elimination rate ratio by concentration is changing. It's not the same. It's decreasing. Contrary to linear pharmacokinetics. Linear pharmacokinetics, the equation was that elimination rate equal to K times dose, K elimination times dose. So the elimination rate and equal to Ke times volume of distribution times Cp, isn't it? So rate of elimination divided by Cp equal to clearance, which is Ke times Vd. The clearance is stable, constant volume, constant amount, equal to constant multiplied by constant. K is constant, clearance is constant, Vd is constant. This one in linear pharmacokinetics. In nonlinear pharmacokinetics, the clearance, which is equal to elimination rate divided by concentration, is decreasing. It's not constant. So here, again, we can notice that with changing the dose, the value of pharmacokinetic parameters also change. So now we'll see how to calculate drug elimination concentrations from certain dose required to achieve certain concentration in case of one compartment model, IV bolus injection, but capacity limited pharmacokinetics, which is Michaelis-Menten kinetics. The equations we use here are elimination rate is equal to Vmax times Cp divided by Km plus Cp, the same. This one can be, from this one we can derive elimination rate by Cp is equal to clearance. Okay, so you can get from the same equation, this equation, rate of elimination divided by Cp means you move Cp here down. So the remaining will be, and rate of elimination equal to clearance. Rate of elimination divided by Cp is equal to clearance. So clearance is equal to Cp divided by Km plus Cp. This remaining part. Okay. T half here is not constant. It is concentration dependent. It's equal to 0.693 divided by Vmax times Km plus Cp. So the higher the concentrations, the longer will be the T half, right? So concentration increase, T half also will increase. So T half now is not constant value anymore. In linear pharmacokinetics, always T half have the same value, whatever the dose we give, whatever the concentration achieved. But here, T half value change with the dose, change with the concentration. Become dose dependent and concentration dependent. Okay? For drug elimination, also the time required for amount of drug in the body to drop from D1 to D2 after an IV bolus injection can be calculated using this value. Definitely, when you have oral doses, then you have to use F also, bioavailability fraction in the equation. But here, this is the equation to calculate the time between two doses, D1 and D2. And it's not depending in linear pharmacokinetic, the time is depending only on the ratio between the doses or the ratio between the concentrations achieved divided by K. But here, the difference between them is there in the term. So it becomes also dose dependent. Okay? And you divide all by VD. You replace the dose by Cp times Vd, so we multiply Vd by C. Then you get another form of the equation. Time to decrease the concentration from C1 to C2. You will have the same equation, but you have Vd in the equation. So what's the effect of Vmax and Km on drug elimination? Here we will calculate the concentration versus time, and then concentration, or you multiply by Vd, you get the amount of drug in the body versus time. If you give a dose by IV bolus, then it's going to decrease due to elimination. But how fast will be the decrease? It will depend on Vmax. If you see the equation for elimination rate, the same equation in the previous slide, okay? If you see the equation, Vmax is in the numerator. So there is direct relationship between elimination rate and Vmax. Higher Vmax means higher rate of elimination, right? So if Vmax is higher, rate of elimination higher, then there will be rapid decrease in the amount of drug in the body. So this is the same amount. The starting amount was same, say for example 300, or say 400 milligram. And then say this one is, for example, 60 milligram. To decrease from 100 to 60, if Vmax is higher, it needs only about 2.2 hours. But if Vmax is lower, it will need 4.4 hours. Okay? So now you decrease the Vmax by half, the time to eliminate will be longer, means rate of elimination became slower, decreased to the half, right? And if you see the equation that will calculate the time to eliminate certain amount of drug or decrease concentration, let's remove Vd, write it as T equal to 1 divided by Vmax times D1 minus D2 plus Km multiplied by ln D1 divided by D2. So Vmax inverse relationship with the time. So the higher the Vmax, the shorter the time, the lower the Vmax, the longer the time to decrease by a certain amount. Okay? So you can see here, Vmax is less, then the time is longer. Km is opposite. Km is the denominator. So there is direct relationship with the time. So Km larger, the time will be longer. Km larger, then it take longer time to decrease from certain amount to the same amount. Okay, so here taking about 2.2 hours, Km larger taking about 2.8 hours. But the effect is smaller. The effect is smaller. You double the Km, but the time will not be double. The time will not be double. Okay? Why it is effect is smaller? You look at the equation. Km is multiplied by another fraction. It's not direct. And added even multiplied by another fraction, then added to certain amount. So the contribution is less compared to the one that is standing alone. Okay? And then the effect of Km on drug elimination, definitely increase in Km will result in decrease in drug rate of elimination. Increasing the Km will result in decrease in the rate of elimination. So patients with a smaller Km, so inverse relationship, smaller Km have greater change in the rate of elimination when plasma drug concentration change compared to subjects with higher Km. Okay, so here an example of rate of metabolism when Vmax is constant, Km is changed, Km 2 milligram for the top curve, Km is 4 for the lower curve. So Km is higher, Km is higher here. Okay, so as we show in the equation, Km has inverse relationship to the elimination rate. Okay, so larger Km, the smaller the elimination rate. This is not concentration, if you notice. Here in this curve, we plot concentration against rate of metabolism, not rate of metabolism here, right? Okay. So if you see, with increasing the rate of metabolism, it's not concentration versus time, concentration versus rate of metabolism. So the rate of metabolism with lower Km will change more with the change in concentration. Will be affected more. Okay, will be affected more by the change in concentration compared to lower, compared to higher Km value. Compared to higher Km value. So the lower the Km value, the higher the change in rate of metabolism with the change in concentration. Almost done. We just saw examples for calculations. And then the coming lecture, we just see the graphic methods to determine the Vmax and Km. Okay, so now we just end up with two examples for calculations. So the first example is a drug eliminated from the body by capacity limited pharmacokinetics, means Michaelis-Menten kinetics. Km is given, Vmax is given. If 400 milligram of the drug is given to a patient by IV bolus injection, calculate the time for drug to drop to 50%. Calculate the time for drug to be 50% eliminated, means amount to be dropped by 50%. So first was given 400, 50% means you want the time to decrease to 200. 50% is 200, right? So D1, 400 milligram. D2 is 50% times 50% equal to 200 milligram. So just apply the same equation, time equal to 1 divided by Vmax D1 minus D2, which is 400 minus 200. We put the value of Km, 100, and then D1 divided by D2. So it will take about 5.39 hours. So if 320 milligram is given, same drug, 320 milligram, I wanted to decrease by 50%. So means that D1 is 320, D2 is half, 160 milligram. So how much will be the time? Is it the same? If we are talking about linear pharmacokinetics, it will take the same time as one half-life, right? Half-life means to drop from certain amount to half of this amount. So actually this one is the T-half when the amount of drug in the body is 400 milligram. Let's calculate here the same Vmax, same Km, but the D1 and D2 are different. You get a different value. This here actually we are calculating T-half when the amount of drug in the body is equal to 320. So when we increase here, the amount is 4.59. So what happened when we increase in this saturable metabolic pathway or capacity limited, if you increase the amount of drug in the body from 320 to 400, the T-half increased from 4.59 to 5.39, means the elimination rate decreased. So here you can see that T-half change and elimination rate also changed with the increase in the amount of drug in the body. Okay, so what is the explanation? It is capacity limited elimination. The half-life is dose dependent because the drug process is partially saturated. Therefore, small changes in the dose will produce large differences in the time for 50% drug elimination. Parameters Km and Vmax, these are the parameters that determine when the dose is saturated. It depends on Vmax mainly. Okay. For the same example, also calculate the time for 50% elimination of the dose when the dose is 10 and 5. So 10 and 5. 10 means D1 is 10 and D2 is half, is 5. Right? And 5 means decrease by 0.5 means the second amount is half, 2.5. You can see here that amounts is very near to each other. Okay. Why? There is no big difference with the change in the amount here because as we said at the beginning it is linear pharmacokinetics, then it will deviate. Right? So before saturation point, at low doses, at low concentrations before saturation point, there will be no much change in the value of pharmacokinetic parameters. We stop by here. The remaining part, about 5 or 6 slides only, we can complete in the tutorial after Eid inshallah. And have a good and blessed Eid. Salamat Hari Raya. Any question before I close?